We are now at the final section of chapter 1. In this section, we learn a few techniques to construct new distributions and try to study the probability function of the new distribution. For today's lecture, we have about 20-some minutes left, and it's definitely not enough to finish this section in details within 20 minutes. So what I'm going to do today is to go over this section, at a slightly broad level, meaning we will discuss or introduce the notations, the definitions, and give more intuitive explanations of everything. And in the next video, we will fill in with details, like 2 examples, 2 proofs, okay? So the first thing I want to talk about is compound distribution. This will be an extremely important concept later on, especially in chapter 3 when we study the aggregate loss, okay? Here, let's study the first idea of compound distribution. So here, xi is a sequence of IID random variables. So they have the same distribution as x. Let's define a new random variable s by this. So it's a summation, but unlike regular summations, here the number to be summed is unknown. So here, xn is actually another random variable, which basically controls the number of random variables to be summed up. So basically here we want to, we don't know how many x's we have, right? So if this capital N is a constant, a small n, then we go back to the standard summation case, okay? So here we have compound if the number to be summed is another random variable. So here we have 2 random variables, okay? So the n is called the primary distribution. The primary distribution is the number of random variables x's to be summed up. And the second distribution is about x, okay? They all have the same distribution, so it's x. The second distribution, well, we simply call it secondary distribution. So it's random variable x. So if I want, I can write this as x, I from 1 to capital N, which is a random variable. It's called the primary distribution, xi. Of course, n may be 0, right? The default summation is if you sum up from 1 to 0, you return 0, okay? So this is kind of like a convention, okay? So when n is 0, obviously s is 0 because you have nothing to sum up. So that is the definition part, right? So when n follows Poisson distribution, and we have a special name, we call it compound Poisson model, okay? Later on in chapter 3, in most of the cases, what we study is a collective risk model, which is essentially the famous Kramer-Lundeberg model of the aggregate. Under the current setup, obviously, we cannot apply the result from chapter 3 right now. What I can give you is a simple example, okay? So right now, let's say we are actuaries for an insurance company. What we are trying to model is the total claims of this company's policies in next year, okay? Because we are talking about next year, 2 things are uncertain. So the first thing is we don't know how many policies our company will be able to sell in next year, right? Because it's the number of policies in next year, right? So we may have new customers, we may have some customers leaving our company. That means I don't know how many policies we will be able to sell in next year, right? So the number of policies is unknown at this moment, right? And for each policy, how many claims it will incur is also unknown. So I use xi to denote the number of claims for policy I. So xi denotes the number of claims for a particular policy. So in this specific setup, What we don't know is the number of policies and the number of claims for each policy. So that fits exactly what we are trying to do here, right? In that example, S will be the total number of claims to our company in the next year, right? So in this particular example, we do need to sum things up, and how many we sum up is also unknown. And of course, later on we will see this compound distribution is particularly important in chapter 3. Okay. So the degenerate case obviously is when we know exactly what n is. So when we use small n, that means we know it takes a specific value. The easiest of the degenerate case is obviously when we have n equals to 2. We sum up x1 plus x2. So this is the standard convolution, and this twofold convolution. Twofold means it's x1 plus x2. Threefold means it's x1 plus x2 plus 3. Okay, so by the same language, we have n-fold, right? So x1 plus x2 all the way to xn. Okay, since we consider non-negative integer values, so this formula is rather trivial to see, right? So in order for my summation to be s, one of them will be x, the other one will be s minus x, and x has to be between 0 and s, right? So nothing fancy from this formula. Then we have an example. Okay, at this moment, I would like to ask you to complete this example. Okay, it shouldn't be complicated, right? So we have, I ask you twofold and threefold. So you start with twofold. In order to get twofold, you can easily apply this definition or this formula, right? So once you have twofold, threefold, x plus 2 plus 3, you can think it is twofold plus additional 1, right? So basically, you are still working under the regime of two-dimensional, right? One random variable add to another random variable, right? So given that you know twofold, threefold shouldn't be complicated. Here, I would like to basically remind you that when you do the convolution, make sure you exhaust all possibilities, right? Do not miss anything. And when you get to the twofold convolution of x, do a quick check, meaning summing up all the possibilities, right? You're supposed to get 1. If the summation is not 1, you are missing something. Or if the summation is bigger than 1, you are overcounting something, right? So remember to check your result. Okay, I will show you how to do this example in the next video. Then we have theorem 5. We apply theorem 5 a lot of times, okay? Maybe not in this chapter, but definitely in the future. So it's important to know this result, and a prerequisite of this is the Tower rule. The Tower rule of conditional expectation. The first thing I would like to point out is the conditional expectation of x given y is a new random variable, okay? It's not a constant. Okay, in fact, it's a function of y. So it's a function of the condition, okay? Next, if I take expectation on this conditional expectation, again, because it is a random variable, so it makes sense to take expectation for a new random variable. What I have is the unconditional expectation of x. So I know it's a lot to basically to trust that the conditional expectation is a new random variable, right? Because it used to be the case whenever we take expectation, we get a constant. But now I'm trying to convince you that if you take expectation, given certain condition, this is a new random variable of the condition. Okay, so it's basically a functional of y. That's why, you know, I call it a new random variable. Okay, and if we take expectations for an unconditional expectation, it's basically it's somehow like you cancel one of them, and you get the unconditional. So this is the famous Tower rule. Okay, one way you can understand this is what is the conditioning, right? Let's use an example. Let's say I want to study the grade of this course. Okay, so X now is the grade. But first, I want to separate, you know, you guys into male students and the female students. So Y is gender. Okay, so given male students, I have a grade. Given female students, I have another grade. Right. So here in let me add one page to quickly explain. It's impossible to introduce conditional expectation without measure theory. So the best is I can try to use examples. So let's say X denotes the grade, okay, of a student. Y denotes gender. Okay, so Y takes two values. Okay, so male or female. So use capital letters. Okay, X is a numerical grade. You know, let's say between let's say it's between 0 and 100. Okay, so what is the meaning of E of X? Right, this is basically the average grade. Right, so let's say I have maybe 100 students in this class, then the expectation of X will be the average grade, right? The average grade. Okay, now I don't want to calculate the average grade directly. Okay, I want to introduce more into this analysis. One way to do it is to introduce a second random variable. Okay, now what I want to study is X given Y. Okay, in this particular case, Y is very simple. Y can only take two values, right? So what I actually study is, so here are the male students, right? So that means right now what I'm trying to study is the average grade for male students, right? So the meaning is very clear in this case. This is the average grade of male students. Okay, Y can be female as well. So in this case, the meaning is, well, similar, right? So instead, this one right now is the average grade of female students. From this simple example, did I convince you that X given Y, the conditional expectation, is a random variable? Because now it's not a single constant, right? So the value of this conditional expectation actually depends on the value of my condition, right? So here I have two possible conditions, male or female, okay? Given male, there is a value. Given female, there's another value. So I'm talking about the random variables, right? So this, let's assign value. Let's say this is A, this is B. So this is A when Y equals male. This is B when Y equals female, right? So it is a random variable. It's not a constant, right? A and B are likely to be different, and even they are the same, it's still a degenerate case of random variable. And in most scenarios, if you assume the grade has something to do with gender, then A and B should be different, right? In that case, it's definitely a random variable, right? It's not a constant if A and B are different, right? And it's a function from the possibility or from the scenario of Y to a real number, right? So when we speak of this, it's actually a mapping from the, this is the sample space of Y, right? two real numbers, right? Although here we only have two numbers, right? But they are, well, this forms a subset of real numbers, right? So right now what we have is exactly random variable. Random variable maps from some sample space to real number, right? So that's why here hopefully I convince you that the conditional expectation is a random variable. It's not a constant, right? So now I'm trying to convince you the second concept, that if I take expectation for this, it will be A times the probability of male. Again, now this is a random variable regarding y, right? So we can think this as a function of y, right? So when I have A is the probability of male, then when I get B, that's the scenario of female, at times by the probability of female. Okay, I claim this is the same. Okay, if you don't believe, you can just do another easy example. Okay, so assume I have 100 students. Let's say 60 of them are male, 40 of them are female. Okay, how do I calculate the average? Okay, so let's say I want to know the average grade. So now, right now, what we have is, hypothetically speaking, I want to do this. Okay, this is one way to do it. The other way, of course, this is slightly different from this formula, but the idea it's something that really matters. Okay, this is one way to get the average, right? This is the average for all students. Right now, okay, I want to do male first. So assume the first 60 students are male. Okay, this is given y equals male, right? Okay, let's do the remaining. This is given female students. Okay, now let's look at this formula. Okay, the percentage of male students is exactly 60%, but I don't write 60%. I write as 60 over 100. Okay, times this. Okay, plus 40 over 100 times the conditional mean of all female students. Okay, now I easily cancel those. What do we have? Exactly one, right? So I hope this example convince you that you have those two results. Okay, we really need those two to prove this. Let me give you a hint, okay, to see whether you are able to prove this result. The left hand side is S, and by definition, S is summation from 1 to capital N xi. Okay, obviously it's unconditional expectation. I'm going to condition this on how many n's, how many x's I have. Okay, this is nothing but the Tao rule, right? So now x is the whole exponential term down here, and my y is the number of claims or the number of policies. Okay, when you condition on n, you treat n as a constant, right? So the inside part, n is no longer a random variable; it's a constant. Only when you take the outside expectation is the expectation of n. Okay, there's another thing we can tell from this particular example, right? When we take the outside expectation, is the expectation regarding y, not x anymore, right? So we have already dealt with x for in the inside conditional expectation. Okay, let's move on. This example is it's rather straightforward. We just need to apply this result, and to get to the probability function, we differentiate, right? So this is nothing but the probability generating function at 0. And this is nothing but the first derivative of the probability generating function at 0, right? So it's an application of the results. So this is a very helpful result from the Panjer's recursive formula. This is very famous. Panjer is a very, very well-known researcher in actuarial science. He's also one of the authors of the SOA reference book, Loss Models. I think he retired from the University of Waterloo after teaching and researching there for many, many years. Here we have this nice result. So first of all, we still work with the compound distribution. So the basic setup is we have this. If n belongs to AB0, so we have several candidates: binomial, geometric, negative binomial, and the Poisson. Right? It is if n is one of those distributions, and x is non-negative integer value. That is a strong assumption. Okay. In that case, I can calculate the probability function of this S. Okay. In many cases, it's rather difficult to figure out the convolution, exact convolution. Okay. And here, Panjer gave a beautiful formula. It's a recursive formula. The starting value usually is very easy to calculate. The value at 0 is very easy to analyze. Okay. And the nice thing of this is once you know the value at 0, you can apply this formula to move to any point you want. Okay, that is the beauty of this formula. It's fully explicit and it starts from 0. Okay, proving this it's rather tricky, and we will not do the proof, but it will be a good idea to know the result. I believe it is also part of the test question on the SOA syllabus. So it's tough to memorize this formula, okay? We will have some results or some examples on that. Example here, theorem 7 is very, very important. We need those a lot. We will prove this in the next video, okay? But now let's take a look at the intuition. Again, let's start with this constant case. So at least for expectation, it's very, very easy, right? It's nothing but n times the mean of x, okay? Now we don't know n. N is another random variable. What do you expect? If you know the exact value of n, it's simply n times the expectation of x. Now we don't know n. N is yet another random variable. So the best we can expect would be replace this n by the expectation of n, right? I think that really makes sense. Variance is more complicated. That is because the variance is non-linear, okay? It's second order. So things get more complicated. You cannot directly apply the intuition from here because here it's simply the n times the variance of x, right? And if you change from a fixed constant to a random variable, not only you have these things, you somehow expect, right? And still you have a second correction term, okay? We will need to apply the conditional expectation formula to prove that. The example, I leave that to you. In particular, part B is a direct application of the previous theorem, okay? Part A is to apply Panjer recursive formula. So try those first, okay? I guess I will probably stop here and will resume in the next video.